哎，这个要找的是不是可以？所以这个 P 是那个 basis，然后这个对 D 是那个找完后的 A，对对对对，OK。等一下我还会再讲多一次这个例子，类似的例子，我还会再讲多一次。我等一下还会讲多一次。那个好难的，这个希望不会啊。嗯嗯嗯，
你看，它什么意思？这个定义是这个，就有时候 P 下面加标，有时候不加，我就觉得
哦对，因为你看他这里有写，他这个是他自己定的，他自己定义的。他说 P 是这个 PB，然后这个 PB 呢是在4.4。其实它这个 PB 就是我们那个 PB 去 BS，
，B 对
对，B 要 B 分的，对。然后你看 B 去 B center 就给回你这个嘛，对，
就所有的 T，它都是这种情况。
什么意思？
就为啥所有的哦，它这个就是通的情况，就是所有的情况这种状况，
对，
这种感觉。
没有错，
嗯，好吧
没有错，
，OK。
嗯嗯。 It's 罗庆瑞 Okay. Okay. All of you like get sick. I got message. So please take care of yourself. We got exam coming next Tuesday. Okay. So set your calendar alarm for next Tuesday morning. So good afternoon to everyone. I realized that last week we got a little bit abstract. Okay. And maybe we got a bit fast for you. And try to stop me when I go fast. Okay. So I know that some of you might maybe you want to listen first before you ask. Maybe you try to figure out. But I give you a choice that you can stop me anytime. Okay. Anytime you like. You just stop me if you want. Over the weekend, I get more questions from you, especially from Fang Hao, right? Fang Hao. Yeah, Fang Hao. Yeah, I got some mistake in my solution, so I already corrected. Please check again. If you got more mistake, please tell me. So those mistakes are very important. They lead to some important concept problem. Let me bring the definition up. So as I say in the announcement, for tomorrow quiz, there will be nothing like proving definition of pure max definition, but we will have a question using various theorem. So make sure you understand the theorem, not proof, but how to use it. What's the meaning of the theorem? Okay, so let's do some recall or revision here. Okay. First thing I want to look at is the definition of orthogonal set and eigenvector, and also definition of diagonalizable. And then I will show you one example of change of basis. Because if you look at my solution, I'll draw a lot of square with arrows. Maybe you don't know what I'm doing. Okay, I will show you in concrete example now, in easy case, 2x2 case. But before that, let's talk about this orthogonal set here. Okay, so a set of vectors is said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. Okay? Namely, when you check the inner product, you get 0. But can the set contain a 0 vector here? No. Actually, it can. Okay, so actually it can. Orthogonal set can contain 0 vector. Okay, because there's no sentence that says non-zero vector here. There's no non-zero vector here. Okay, so you can have zero vector in the set, in the orthogonal set. For example, I'll give you an example. So for example, 1, 1, and 0, 0 is an orthogonal set. Okay, but remember
in the examples that we do, we say that if they are orthogonal, they are linearly independent, right? Remember? Actually, in that example, all the vectors are non-zero. Okay. So if we examine this theorem again, okay. So the theorem here actually states if X is an orthogonal set of non-zero vector in Rn, only then it is a linearly independent set. Okay. So not all orthogonal sets are linearly independent sets. All right. So make sure you make this clear. And the second part is eigenvector. Okay. Eigenvector. So can eigenvector be a zero vector? Cannot. Okay. So eigenvector is a different from orthogonal set. So eigenvector must be a non-zero solution to x equal to lambda x. Why? Why? Because a times zero vector, what do you get? You always get zero. And you can put any lambda on it, right? Like any lambda times zero vector, still zero vector. So what lambda you want to pick? Cannot decide. So we throw away zero vector. Okay. So eigenvector must be non-trivial. So 0, take away here is zero vector and not again vector. All right. Okay. So this is the important part between orthogonal vectors and eigenvectors. Next part we talk about diagonalization. Okay. So actually really what diagonalization doing is change of basis. Okay, so I really want you to get this part. Even though you're not a math student. Okay, so let's lay out the so what is a change of basis or diagonalization? Diagonalizing really. Okay. So I want to use a concrete example, the example that you every time do. I want to tell you what's the process inside there. Okay. So let's say, okay, let's say we got a matrix A. Okay. So a matrix A from 2 weeks ago, matrix is equivalent to what? Matrix function, linear transformation. Okay. So you can think of it as a linear transformation, sending a vector to another vector. So this is a 2 by 2 matrix. It's going from what space to what space? 2 by 2 matrix going from which space to which space? R2. Okay. So we are now consolidating every knowledge we have now. Okay. So usually I will put space arrow like this, and then on the element I will put this kind of arrow. It's like map2. Okay. The latex code for this is map2. Map2. And this is element, this is space. Okay. Right. Okay. So after you see this, okay, after you learn last week material, maybe you want to diagonalize it. Okay. Maybe you still don't know what is diagonalizing doing, but try to diagonalize it. So what do you do? If you want to diagonalize it, what do you do? You get the determinant of A minus lambda I. Okay. So which is the character? Wait, let me put something here. So to diagonalize it, like first find the characteristic characteristic polynomial. down. Okay, so in this case, I told you what is it. So in this case, I told you it is lambda equals to 2 and 3. Even if I don't tell you, you should be able to see from the diagonal entry because this is a triangular matrix. Okay, good. So second part, after you do this, how do you find the eigenvector? You compute the null space for every lambda. Okay, so compute the space minus eigenspace of A minus lambda I for all. Okay. So in this case, I also tell you what are they. So there are V lambda, oh sorry, V lambda equals to 2 is 1 minus 1. V lambda equals to 3 is 0, 1. Okay. If you don't want to do row reduction, in a 2 by 2 case, you also can guess. Seriously. For example, you want to make this 3 pop up, right? So what vectors you multiply by this vector, you have 3 times that vector. The easiest one is 0, 1. Okay, so you make everything harder than the 3 disappear, and then you will get 3 times 0, 1. Maybe 1 minus 1 is a bit harder, but if you do more exercise, you can see quite quickly. Okay. By 2 is easier. Anyway, but I just tell you what is it first. If you want to do calculation, you can do it on your own. So now, by a diagonalization theorem, A equals to just 1, 0, 1. Okay, this is the P that we always call it. And then how you put the D, you need to align the diagonal entry with your the position of your eigenvector. So the first one is correspond to 2, the second one is correspond to 3. Okay, and then find the inverse. So this one inverse is also not too hard to find. Just apply the 2 by 2 formula. Formula is 1 because triangle. So you swap A and D and then put minus on B and C. Okay. So what's this doing? Okay. Why are we inverting this? Okay. So remember the story at first. We want to see it as a linear transformation between vectors. Okay. That means we apply this matrix to a vector. Okay. Let's apply this matrix to a vector. Let's see what's going on. What happened to the vector? Okay, let's see what happened to a vector. And I want to pick 5, 7. Okay, let's pick 5, 7. Let's see what this matrix said on this. You know what happened to 5, 7? What happened to 5, 7 after applying this matrix? Huh? Yeah. I mean, what's the vector it gets sent to? Can you compute the vector? Yeah. 10 and 26. Okay, good. 10 and 26. Okay. So in this case, this is what I draw in the arrow there. So I will write 5, 7 gets sent to 10, 26 by 2013. Okay, this is what I always draw it here. Okay. So try to make this arrow concrete now. Okay, so this is not fun. Okay, because this is just matrix multiplication. Okay, so what's really going on is if we can express 5, 7 in terms of the eigenvector basis, the calculation will be easier. Okay, let me show you. So how you express 5, 7 in terms of minus 1, and 0, 1. Do you have any idea? Okay, let me put something here. So BV lambda is 1 and minus 1 and 0, 1. And then the standard basis for R2 should be what? 0, 1, 0, and 0, 1. Okay. Let's say we pick a different basis. Okay. So this means we can express any vector in terms of the vector inside the new basis here. Okay. So what's the coefficient? What's the coordinate vector of 5, 7 in this new basis here? Any idea? Huh? 10, 13, 13, or 12? 12 or 17? 13. 12. Okay. So this is what? Okay. Yeah. Okay. So why is this easier to calculate? Okay. What happened? What happened to this calculation here? Okay. So if you open it up, it's a matrix on an eigenvector. Right. Matrix of X eigenvector. Do you still need to do matrix multiplication or not? Only right. This matrix times its eigenvector become a lambda V. Okay. So first one is the eigenvector that correspond to 2. Okay. So become 2 times the eigenvector plus 2 times 3, 12 times 3 times the eigenvector. Okay. Okay, in case you log again, so I like write down because 1 minus 1, 0, 1 are eigenvectors of the matrix of A. Okay. So here I've read things 5, 7 in terms of V lambda is equal to. Okay. So you see the calculation just now is row times column. Now the calculation is just coordinate vector and then the scalar coming from the eigenvalue, right? You get what I mean? You see? You see? Okay. But in this case, what do we get? We also get the same answer. 10 times 1 minus 1 plus 36 times 0, 1, which is equal to 10 and 6. It's the same. Okay. Maybe you will see that, hey, here got 3 equal, here only got 1 equal. Maybe the first method is easier. But let's say your matrix is like million times million. How many multiplication and how many addition you need to do for matrix multiplied vector? But this one will always stay the same. Maybe the process will get harder when you compute this, but it's not as hard. Okay. So in the diagram language, what that I drew is, let me phrase the whole process in a different way. So let's start with what we have. We have R3, R2, okay, a map going from R2 to R2. We call it A, okay, and then we send the element in R2 to AX, okay. So in just now, the case we have is what? The case we have just now is 5, 7, and 26. Okay. So let's say we change our basis to the eigenvector basis. I just quickly run through this diagram, and then you can compare to what we did just now. So if we change the basis to the eigenvector basis, okay, and then we take coordinate vector, and then we compute on the level of coordinate vector. You notice that just now the eigenvector never changed, right, in the computation. Okay. And which we get orange gone. I want my orange back. I put 5, 7 here, and then put 10, 26 here. And then we go downstairs, we get 5, 12 instead. And then we go the other side, we get, let's call this horizontal arrow D, and then we call this D on X, which we compute is 10 and 36. Okay. Yeah. Okay. So the bottom here also has space, right? So the space at the bottom is also 2. Okay. So what we did is we go down, we go across, and then we go up. So this is the A equals to P D P inverse. Okay. So if you really want to spell out which step we are in, can I move this down? Okay. So the first step, in this picture here, we show the vector in terms of coordinate basis. So this is the first step we do here. Okay, this is the first step. Second step, we have this D here. Okay, so this D here really is this part. Is where you pick up these 2 and 3. Think about it. If you think about it. Okay. And then the 3 here is the last arrow here. Okay. Yeah. So I put this correspondent here, and then you try to understand. Okay. And then try and look back the previous tutorial, see if you can understand the arrow I drew here. Okay. If you really, really cannot understand, you can give up. Yeah. I mean, yeah. If you really don't understand, you can give up. Try to learn other stuff. Yeah. If you really want to know, I already draw up all the arrow, what's the correspondence between the real step and the arrow in the diagram. Okay. If you're still struggling to know, you can come and find me again. Okay. Yeah. No, nothing. Okay. All right. Okay. Yeah, this is really the essence of the diagonalization. Okay. It's not just about making your matrix into a diagonal matrix, but make a change of basis so that your calculation will be easier. Or change of basis, become a different matrix. Okay. But for your course, you just need to know how to diagonalize. That's all. Okay. Right. Let's jump into today's content. So last week I think I skipped this part here, the orthogonal complement. So maybe we need to bring it up a bit. So the abstract part of this how to say this object here won't be tested, but just language. Okay. So what's the language here? So let's say you got a subspace W. Okay. The orthogonal of complement of the W. So you should think of it something that's 90 degrees to this subspace. Okay. So what is it? So it is exactly those vector when you take inner product with your element in the subspace, you get 0. Okay. So some easy example here. Okay. Easy example. So for example, a 0, 0, 1, sorry, is orthogonal to 0, 1, 0 and 1, 0, 0. Can you see this? Try to take inner product. If you take inner product, you get 0. How to easily see it? Because the 1 appear in different spot. Okay. 1 appear in the last spot, second spot, and third spot. So when you take inner product, they won't match up. Okay. So 0, 0, 1 is orthogonal to these two vectors. In particular, 0, 0, 1 is orthogonal to all vectors in the span of 0, 1, 0 and 1, 0, 0. And see this? See this? Okay. So 0, 0, 1 is span. So what's this picture here? So the picture here really is, you can think of it as the V here is orthogonal to everything on the plane. I draw right. Okay. So you can think of it 0, 1, 0, 0, 1, 0, and 1, 0, 0. The span of two vectors, okay, is orthogonal to 0, 0, 1. Okay. So is it okay? Okay. Make sure you stop me, because yeah, so yeah. W is just what? Is a what? Oh, it's just a line. Okay. No, I haven't finished yet. Sorry, I haven't finished yet. I just talked about one vector is orthogonal to a subspace. Okay. But now this W per, okay, this thing is called per. So this thing is called per. So W per is a subspace, right? So how is it a vector, a subspace? So you need to take the span of it. Okay, so you take a span of it. So finish it. So there are two sentences, third sentence here. So span of a single vector is equal to the perp of okay. So if you consider the line passing through the plane, this becomes subspace, and then this subspace is orthogonal complement of the plane. Okay, right? Yeah, just some terminology. I think we already see these kind of objects. Keep seeing it. Okay, just we give it a name because we want to have some structure or theorem. Okay, all right. So okay, this is exactly what it is drawn here, but it rotated it. Okay. Okay. So this theorem, frankly speaking, not important, but you can studying it for your own sake. So this result also already clear to you, but we studied it different way. So for the first one, let's take a m by n matrix. It says that the orthogonal complement of the row space of M of A. So let me draw the matrix for you to imagine first. So we got a matrix here, and then M times N. Okay. So the orthogonal complement of the row space. So row space meaning I have to draw some row. So maybe draw like this up to E M. Okay. The orthogonal complement of row space of A is a null space of A. Think about it. How you compute null space? How you compute null space? Let me remove this. Okay. How you compute null space? You put your X here, right? And then you do row times column. Right? Isn't this an inner product? Is this an inner product? Not obvious. Inner product. So you got row times a column. Right? So this is an inner product, right? Okay. So this X is the X that satisfy XW, where W is the row vector here. Okay. Let me put something here. So okay. So let me to align with the definition, we have W as the row space of A. Okay, so W as the row space of A, meaning you take the row vector. Okay, you take the row vector, and then W put here is the null space of A. So this means when you take null space of A, inner product with the row vector, you get 0. Inner product with the I wonder, should I? Let me see. Okay, so let's take a thing inside the null space here. What's the null space here? What's the null space here? First thing I should put 0. If I put 0, I should put 0. Okay, anyway, I put 0 here. 0 is a subspace. Okay, so how do you get 0? So row space is what? Row space is 2, 0 and negative 1, 1. Okay. Null space is this 0, 0. Okay. So when you multiply it, what do you get? You get 2 times, let me put this as the blue one, 0 times 0. Okay. So isn't this the inner product between the row vector and the column vector here? Right. The following column. Okay. Okay. So similarly, -1 times 0 equals to 0. Sorry, 0 times 0, which is equal to 0, 0. Yeah. What's going on? And most of you are blue. And yeah. Okay, one possibility is you still not familiar with this the definition of this word here. Okay, one tips I want to teach you to learn maths. Not only learning maths, it's also for your work. It's the same. Okay. Okay, let me tell you one story. So previously when I watch English movie, right, I always fall asleep. Okay? Because I don't know how to watch. First is the language problem. Second is I can't understand how their story goes. Okay. But after I think almost finished PhD, somehow I realized I know how to watch the movie. Yeah, seriously. That means there's some change in my thinking. Okay, and then I try to think what changed. Okay, so mm, what changed is one of them is I try to accept what people say first. Okay, regardless who it is correct or wrong. First, understand what he's saying and listen carefully what that person is saying. Okay, don't think about it is reasonable or not, is correct or not, is right or not. But first, understand what he is stating first. Statement. So statement in mathematics is very important. You need to know the statements first before you make true or false. If you can't even understand the statement or listen to the statement carefully, then you cannot make decision whether it is true or false. So first step is to listen to the statement first. Okay. If you don't understand the statement, that's what I ask you to do. So ask me, stop me. Okay. Okay. Listen carefully what people say first. Okay. Before thinking about it, true or false or why is it. Okay. So first of all, listen carefully what people say first. Okay. Yeah. Okay. So if you don't understand what that people is saying, ask what is that thing. Okay, ask what's that thing, what's that thing, what's that thing. Okay. But first importantly is you listen the statement that people make. Okay. This is the most important before you make any result. Okay. Do you want me to go through this theorem or go through this? Feel like I have nothing to say more. Okay. So what's the definition of orthogonal complement? So orthogonal complement of a subspace. Okay. So when I say orthogonal complement, must be of a subspace. Okay. Complement of what? So of a subspace. Okay. So this means you need to give me a subspace first. Okay. So he give you a subspace, row space of A. Okay. So now you need to start imagine row space of A. What is row space of A? Okay. Row space of A is the row vector in your matrix. Like this row. Okay. So you have to start thinking row space of A. So what is the thing that when you take inner product with this row space of A, you get 0? Huh? It's the null space of A, right? Right? Correct or not? Row times column get 0. Isn't it the null space of A? Right? Correct? Yeah. So when I say one word, you need to change into your imagination. Okay. So most of the time, when people fail to communicate, is they think differently. So when you want to communicate on one table, you need to speak on the same thing. Okay. Yeah. Yeah. You mean the basis of null space of A is the basis of orthogonal complement? Yeah. You can say that. Yeah, because the two space is the same really. Okay. The second one, maybe I skip it. It is an application from the first one. Application from the first one. Okay. I will write down why it is true, but I won't discuss it. It is an application of transpose of A from the first statement. Okay. So this one, if you want to know, I leave it as a homework. Okay. Okay. What things 3, 4, 3? Let's okay, maybe I ask you guys first. You know how to do, if not, don't know how to do, then maybe we recall. So let's say if I give you two vector, do you still remember? Okay, two orthogonal vectors. Do you still remember how to decompose y into both of them? How to project y into this 2 point? Remember the formula or not? Now just honestly tell me, is it on top of your head or not on top of your head? No. Okay, I think mostly no. Okay, never mind. So maybe let's redo again because this is very important, and we will accelerate after that. So recall that the construction. Okay, so we got a y, and then we got a u. Okay, and then remember what we did last time. We want to project our y to u, which we call the projection on u and then y. Okay, project y on u. And then if we take y minus the projection of y on u, we'll get an orthogonal vector which is orthogonal to u, right? Where y minus proj of u is 0. Okay? Recall this? Okay. If you don't recall, you have to believe me now because I cannot repeat the construction again. So the story is you have a y, okay? You project on u, and then if you take y minus u, you will get the orthogonal part. Okay. Okay. So who remember the formula? What's the formula here? What's the Porsche formula? Y dot u over u dot u times u. Y times u because it's on the u direction. Okay, and then we extend this to a set. So we extend it to a subspace W, and then of u1, u2, up to un. Okay. And then we can express the proch of W. Okay. Proch of W is equal to can I use CI? Let me use CI and then tell you what are the. This is the thing we saw last time. Theorem. We didn't prove this theorem, but we just accept it, where CI is equal to y dot u. VI. Okay. So meaning we can do for one line, we can do for a plane. Okay, we can do for the whole plane. Okay. I didn't prove that. Why is it true? But it's in the textbook if you want. Okay. So we can extend this. Okay. Is it okay? Yeah. Okay. Yeah. Mm-hmm. Let's say again. Oh, yeah. Sorry. Because hello. Okay. Because I copy wrong for the first few guys, so I become V. So it's actually U. Okay. Yeah. It's U. Expand to a subspace W, which is the span of. So need to be careful here. It's a span of orthogonal vectors. Yeah. Only for orthogonal vectors you can find your coefficient like this. Otherwise, remember what we did? We use the row reduction or we use the Cramer's rule. Right? Only for orthogonal vectors you can use this inner product. Okay, orthogonal set. Okay. Maybe let's do this example before we break. Okay. If we can pass this example, then we take a break and then we go forward. Okay, let's try spend 3 minutes. Try do if you can use the formula and do this example here. So the question not just want you to find a vector, right, y as a vector, project y in the subspace W. It also wants a vector orthogonal to W. Okay, so this means you need to take the difference between the vector. So yeah, later we'll say again, but just to remind you. Assume you have a copy in your hand. You don't need to keep looking at mine. You can have a look on the one. I have answers, so I just copy the answer. Is it almost finished, you guys? Okay. So let's go through. So even if you haven't finished, that's fine. Never mind. Let's go through. So the question say you got U1, U2, and Y. The question asks, write Y as a sum of the vectors in W spanned by U1 and U2, and a vector orthogonal to W. It doesn't tell you whether U1 and U2 are orthogonal or not, right? So you need to make sure they are orthogonal first. Okay, then you can use the method we learned just now. So you need to show that it is orthogonal first by compute the inner product. Once it is orthogonal, then you can use the formula we had just now, where prosh y to the subspace is equal to the coefficient times the orthogonal vectors. Okay. Anyone have problem applying the formula or not? Anyone have problem applying the formula? No? Okay. And then by the theory we mentioned just now, we just take y, take away the project one, we will get something that is orthogonal to the subspace. So we take y minus the projection of y, we will get a vector that is orthogonal to the subspace. Then these two vectors will add up to 1 because it's exactly how you find the orthogonal. Does it make sense? Make sense? Okay. Yeah. Anyone have problem with calculating or understanding how to apply the formula? Okay. Okay. Is that okay? Okay. So how about let's take a break? Take a break until 4:07 and then come back. 我觉得是。
没错，又小错了，那个2，看一下，哎，对，错，底下这边这个
就是从
你要把他们看成一个 PT 线，对，他们每个都是一个 PT，这个 polynomial 就是每一个都是一个 PT 的元素，懂什么意思吗？
就是 PT 可以写成什么乘以一？
也可以这么理解，但是这一题不需要这么做，因为这一题的重点是 evaluate 那个 t 在里面，那个 t 在一，evaluate t 在二。对，意思说，比如说你看 pt 等于 t 的话，100的话，
0。
嗯然后一呢1哦，t2等于2咯，
对，
所以你看我这里10是0，11是1，12是
PT 等，然后 PT 等于 T
对，没有错，
等于
对，没有错，一模一样。
给出来的。
OK
就是
OK，好啊，OK，OK，我这新的版本这里其实有一个这个，如果更清楚一点呢，因为如果你看啊，ET 等于 E 的话，OK，所以
嗯，
那 E 等于什么？
P 等于什么？P 等于什么？
知道
不知道？OK，所以你看这个 PT 是 T，所以 T 等于1的时候就1咯。
可是它这个不是
哪里？哪一个？你看，P0是
它没
零。
有说 PT 等于 T。
哦，没有，你看你这里的元素全部是活在这个世界里面，所以这每一个都是一个 PT 来的，不同的 PT。所以当你看 PT 等于1的时候，P0就是1咯，P1也是1，P2也是1，因为它每个 T 它都是1啊。这个 PT 等于 T 的话，就是这个 T 跟这个 T 变了，yeah，然后 T square 就 T square 的变方。你才有4跑出来嘛，因为2个。
这个意思。
Yep, yep.
5.4是考试重点，
5.4是不是考试重点啊？
感觉这个很难理解，
很难理解啊。
有点难理解。
嗯，
题就是有点看不懂，就是看答案，就是尤其是这个图就非常
对，
那考试的话，比如说写这个过程需要画这个图，
没有，考试过程就是这样子的。
嗯，这个练习
下一个
题里面的类似。
呀，
因为我看网上很多就 B 站上面的里面都没有讲这个5.4，就是他们可能其他的
跳过那个。
对，
啊，对。
都没有讲，我不知道为啥。
其实
第八
第8
题
题我们有跳过，我没有注意到。其实我们的那个虽然它原理在，但是我们跳过解释这个。我没有，我在选这个的练习的时候，我没有注意到。
8题
啊，如果你不要看就不用看，但是它的原理是一样的，但是你会看到它的 D 呀、不是 diagonal，但是它也是清水北式之
就是那个老师你说的那个证明
啊。
那个定理的那个不带5.4吧？就是有那个考试的那个需要证明什么那个定理，要加分理解。
啊，要理解，对，要理解，对，要理解，没有证明要理解，对
哦，
对
哎，就
，OK，好多人问这题。对，因为在不同的，因为它这题目其实它假设你已经知道怎么理解什么是方程啊，假设你已经理解了，就是
说成什么
嗯
T 函数 b，然后什么
嗯
TB，那我有点混乱。
怎么说？
就是这个，
嗯
这种这个
嗯，
这个，
好哦，这个的话，如果你混乱这两个东西，你其实要回去找它的那个定义。比如说这个 TB 啊，应该是这个吧？OK，所以你找到这个的时候，你就要看这个的意思。它其实 OK，还有一个东西要注意的是，这个里面是一个 vector，你拿出来的东西还是一个 vector，但是这个通常是一个 matrix。
嗯，
OK，所以这两个重点的那个也不一样。然后，其实这个就是那个，如果你记得就是那个 D 的那个部分，但是它的重点是说你是在相同的 space 的时候，它就叫 TB。你看，the matrix is a matrix representative of T coordinate，所以你又不知道这个 T 是什么嘛，所以你要再回去看哦。你看，let T be any linear transformation from V to V，所以这个就是 T。所以这个 T 是当你去同样的在同样的空间转换的时候，你出来的这个 D 我才叫做TB。所以你要一个字一个字一个字这样。Hello，什么减 因为我们拿这个减了这个才会出现这个。OK，let me pass this. I think this icon got problem, is it? It's not called A. It's not called A, right? Maybe try again. Okay. Okay. So just now we learned W per, right? Okay. So that means this part is W, and then the other part is W per. Okay. So we split our Y into a subspace and another orthogonal complement of the other subspace. Okay. We project it into two spaces. Okay. So what this formula does is, sorry. So what this formula does is you project into subspaces that are orthogonal to each other. Because they are all orthogonal to each other. Because they form an orthogonal set. Or the theorem here says that if W is a subspace of Rn that has orthogonal bases, okay, then any vector in your Rn can be written as something that is inside W and something outside W, which is in the W per, such that when it is inside W, you can split them into U1 up to UP in the control way, in the inner product way, because they are orthogonal, and then the rest is in the W per. Okay. So this is, if you want to remember this, you just remember this picture here, and then make this U into a subspace. So imagine a subspace. Okay. Something that is in U, and then something that is orthogonal to U. Okay. Expand this U into a subspace. So if your vector is already in the subspace of W, right? When you try to project your vector into W again, okay, do you still get Y? You still get Y itself, right? Because your Y is already in the subspace. And this is the theorem. We won't prove it. We just state it. So if your Y is already in the subspace, okay. So okay. Geometric wise is if this is your subspace, okay, your Y is inside the subspace. So you are paper gone. Let me take mine. So if you got your Y, you got your W, okay, your Y is already on the subspace, right? So you project to the subspace again, it's still the same Y. Okay, so this is what it says. Okay. Got it? Okay, okay. But to show it mathematically, you can see the proof. I'm not sure it's in the book. Okay, next is best approximation theorem. So it says that if you look at any vector in Rn, okay, so Y, the projection of Y into the subspace W is the closest one to Y than the rest. Okay, so how to picture this? So let me show you. So let's have a W here, okay, and then you got a Y here. Okay, so inside the W, okay, you can find any W1, W2, W3. Okay. So which one is the closest guy to y? Okay, which one is the closest one? One is the closest one. And let's say W2 is orthogonal to y. So which one is the closest one? Okay. Which is the closest one? I draw the I draw the wrong angle here. The angle should be here. Okay. So the closest one should be the one that is diagonal, that is orthogonal, and that's the orthogonal projection of y. Okay. Yeah. So you cannot okay. Maybe I shouldn't draw this. Okay, let me try again. So we got a W and we got a Y. We want to find the closest vector to Y. Okay. So how to find it? So the claim is if it is the projection of Y into W, that is the closest one. Okay. So the claim is this is the closest one. Why is this the closest one? Let's say we perturb it a bit, okay? So we don't want to do it like this. Maybe we do it like this. Okay, we do it the other way. Okay. So if we do it in the other way, okay, this is what I'm going to say. Let's see. Yeah, I think I should say it like this. So let's say if I do it this way. So I project it down here. I don't know how to project, but let's say I project it further down here. Okay. Okay. Then this is, let's see, let me put Z. No, X. Okay. So X is already further than proj Y. So let me write it down. So Y minus proj W. The length of Y minus X is greater or is already greater than the length of Y minus proj J. Okay. So how to see from the picture here? Because you can find this length by combining these two lines. Okay. So you can find out that this length actually longer than this length here. So you need to make sure that it is a 90-degree orthogonal projection to find the closest vector to Y. Okay. Yeah. That's okay. Mm-hmm. Seems like not convincing. Not convincing. And later if I show you the calculation, then quite long. Is it not convincing from this picture here? Is this like this is longer, the the distance of this green line here. Okay, the 2 here is longer than 1. So I should put that 2 is greater than 1. Okay. Yeah. So the shortest one is always retained by the orthogonal. This is the statement. This is a statement in the theorem. Okay. I haven't quite explained why, but this is a statement in the theorem. Okay. So for example, just now the question here, same question. So if we have U1, U2, okay, U1, U2, and look at the span of this two vector here, and then look at Y. Okay, I purposely changed this to the same example here. And then ask another question. Find the point in W that is closest to Y. Okay. So this theorem here, right? This theorem says that the closest point in W to Y is exactly the prosh. Okay, it's exactly the prosh. The projection of Y onto W. Okay. So when they ask about the point in W that is closest to Y, you just find the prosh of Y, which we did just now. Okay, which we did just now. So prosh of Y is, there's another property of prosh of Y is it is the closest point in W to Y. So all the other point, right? All the other point, you will find that the length is greater or equal to this distance between Y and approach Y. I just restating the theorem here. Okay, we accept the theorem first, and then if you want to know why, then we'll see why. But let's accept the theorem first. Yeah, yeah. Is it okay? Is it okay? So just now we already found that the closest point, the point in W that is closest to Y by theorem above is the prosh of Y, prosh of Y to the subspace W. Okay, which is equal to, we already calculated, it is this one. Okay, so what's the distance between Y and W? Okay. If you got a W, you got a Y. What's the distance between Y and W? Okay. What's the distance? Yeah, so the distance is just you take the distance, the length of Y minus prosh. The distance Y to W. Okay, actually that should define this. So the distance from a vector to a subspace, right? They should define this distance as the shortest distance. So which means you take the orthogonal projection and then you take the. So whenever we talk about distance, right? Depend on how you walk. Okay. Right. Remember I draw a diagram. So remember I draw a diagram like if you got a 2 point, okay. So what's the distance between these 2 points? Okay. Let's say I walk like this. Is this my distance? Or the shortest one is my distance? Yeah, that's our convention. Okay. We will say that this distance is the shortest path. But for example, in real life, what's the distance between two places? In the map, you can see that the distance is the straight line distance. But if you travel on car, you need to have the road restriction. So maybe sometimes the road will go longer, so the distance will become longer based on the condition on the path you take. Okay, but usually the distance here means shortest path. Okay, usually in maths, distance means shorter path. So if it is shorter path to a subspace, then it means the difference between the vector and the projection, orthogonal projection of y. So let me label this part here. So this is the distance. Okay. Yeah. Okay. So the next part is let's say our orthogonal set is orthonormal. Okay. So when it is orthonormal, the length of the vector is 1. When it is 1, the denominator here will become 1. Because the denominator here is just the length of u. Okay? If the length of u is 1, then this part will become 1. Okay? So the formula will be shortened to this, just y dot u, without the denominator. If the length of ui is 1. Okay, so which is equal to ui dot ui square root. If square root is 1, square also 1. Maybe I put this away. Okay. So if it is orthogonal, then we can use this formula here. Okay. So this formula here is the same formula, but you make the denominator 1. Okay. And actually, what's the advantage of this formula here? Then you can compute it using matrix. Okay. It is just u times u transpose 1. Okay. So let's say our approach y is u-u-t-y. Okay, what is this? So our u, as stated above, is u1, u2, up, up. Okay. So how you transpose it? After you transpose, what do you get? So you get first you get column vector, right? Now you get row vector. So row vector is what? U1 become like this, and then U2 become like this, and then U dot 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 times 1. Okay, is it okay? Yeah. So when you do matrix vector multiplication, okay, it becomes row times column. Okay. So when you take U1 row vector multiply a column Y, it becomes the inner product. Imagine, right? Row times column. Is it the inner product? Row times column, right? Okay, so that's why here becomes this y dot u1 and then y dot u2. Okay, and let me write down. Okay, so maybe I for the sake, so let me put this down. Take care. Okay. Row time columns. So row time columns again. Okay, and then now again is a matrix times a vector. So this is the very first definition that we have. So it's like the first term multiply the first column, second term multiply the second column, and p terms multiply the p columns. Okay, this is the very first definition we encounter for matrix and vector. What do you mean? No, I mean, this is different from what you said. What we do is we just associative. So this is equal to U, T, Y. This is associativity. This is commutativity. We don't swap the order. It's the same order. We still taking the same order. It's just that we do the one at the back first, and then we don't swap the order. We just do associativity here. Okay. Associativity. This theorem, if you miss it, it's fine, because it's just a convenient way when our basis is an autonomous basis, then autonomous basis, then our formula will be simplified. Okay, so formula is simplified when we are autonomous basis. But if you will still remember the old way, which is this way, also can. Still fine. It's the same. Just that when the length is 1, it simplifies the calculation. Okay, and then it provides a new way to see this calculation using matrix vector multiplication. Okay, it's really the same thing, but we just play around with the same thing. So far, okay. It's really the same thing, but just play around with the formula. Okay. Next, Gram-Schmidt process. Okay, this one is kind of important. So make sure you get this. So this one is very important. Okay, recall again what we did. Okay. So we got a y, and then we project it on some subspace. Let's say it's a u, so we project it on u, orthogonal projection, and then we take the difference, and z. Sorry, it's a y minus proj u1. Okay. In this case, we produce an orthogonal vectors. Okay. So now we're not focusing on how to orthogonal project one vector, but we're focusing on what thing we produce. Okay, there are two things we produce here. One is orthogonal projection of y on u. The other is the difference between y and the orthogonal projection. Okay, these two are orthogonal to each other. Okay, so if two non-zero vectors are orthogonal, what they satisfy? Two two non-zero vectors are like this. Two non-zero vectors are orthogonal to each other. What they satisfy? Okay, three. Two non-zero orthogonal vectors. What they satisfy? Two non-zero vectors which are orthogonal to each other. What they satisfy? The first theorem we say in the lecture, at the start of the lecture. They are linearly independent. Okay. Yeah, they are linearly independent. Okay. So when you add enough linearly independent stuff, you will get a if you add enough linearly independent vectors, what do you get? They form what set? What kind of set? If you add enough linearly independent. Okay. If you add in linear, if you add until the dimension of the vector space, what do you get? You get a basis. Okay. So this actually provide a way to find the basis. So okay, let's show you. Okay, so let's say we have two vectors here. Okay, look at the span. Okay, now we want to construct an orthogonal basis. So how to construct an orthogonal basis? Okay, maybe let's draw it up. What is it first? Okay, let's draw it up. Let's draw this thing up. Okay, so maybe let's use this, and this. So one is 360. So maybe here is 3, it's 6. Okay, 360. Yeah, thanks. And then the other one is 122. 122 is where 1, 2, 2, somewhere like here. Okay. So so it seems like they are not orthogonal. Maybe let's check what is what s1 dot s2. S1 dot s2 is what? 3 plus 12, which is 15, which is not 0. Okay, so they are not orthogonal. So how to make it orthogonal? How to make it orthogonal? Any idea? No, linearly independent doesn't mean orthogonal. It's not the other way around. So it's orthogonal of non-zero vector imply linearly independent. Linearly independent doesn't imply orthogonal vector because you can see from this example here, they are not scalar multiple of each other, but they are not orthogonal. So how to produce orthogonal vectors? Any idea? From the story I tell just now. Final projection. Okay. So you project one to the other, and then you take the difference. Then you can find the orthogonal basis. Okay. So which one to take? Which one you want to project onto? Which one you want to project? Two, one. Yeah, both you can. Anything you want. Okay. Anything will provide an orthogonal basis. Maybe they are not the same. Okay. So let's fix one. So which one you want to project to which one? Just say one, we will do one. S2, S2 to S1 or S1 to S2? Yeah. S2 to S1, okay. So let's project S2 to S1. Let's do orthogonal projection. S2 to S1. Okay, so that means you fix X1, right? So the standard step is we call this a new basis V1, V2. So we set V1 as X1 first, okay? And then on the picture is this one, X1 and X2. So we project X2 to X1, okay? Yeah, good. So what do we get? So project S2, sorry, project S, yeah, project on S2 of X1. What's this? It is S1 dot S2 divided by S2 dot X2 times X2, right? Okay. So S1 dot S2, what do you get? 3 plus 12 over 1 plus 4 plus 4 times x2 is 1, 2. So what do you get? 15 over 9 over 1, 2, 2. Which is 5 over 3, 1, 2, 2. So is this your V2? Is this V2 already? Why not? V2? No. You need to take S2, then X2, sorry, that V2 be X2 minus the projection. Okay. But we need to take Y, take away the projection, only this will become the orthogonal part to the to U. Yeah, to U. So that dot U. Okay. 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 So you need to take the difference between Y and projection of Y, orthogonal projection of Y. Then this part is orthogonal to U. Okay. So and then what do you find here? So V2 is equal to two minus the projection. Okay, what's this? Am I correct? Maybe it's correct. It's wrong. Correct or wrong? Yeah, correct. Let me see. Project Y to X1. Hey, I think we did something wrong, right? We swap these two, right? So you want to keep this or you want to change this? We did this because we want to project S2 to X1 should be S2 here, X1 here. So you want to change this thing or you want to change which one? To you. Huh? Actually this one is a projection. There. Yeah, so which one you want to change? You want to change the construction or you want to compute again? Huh? Change the construction, okay, change it. Or change this construction. Let's take X1 to X2. Okay. Then we set V1 to be V2. Okay. And then V2 will be X1 minus this thing. So X1 is what? X1 is 360. You want to get the final result? What's the final result? So 3, 6, 18, 18 minus 10, 8. 10 over 2. Okay, maybe let's check for sanity check whether these two are orthogonal to each other or not. Okay, let's check whether they are orthogonal to each other or not. So the claim here is so let us finish the claim. So V1, so V1 is 5/3 times 122, and then V2 is maybe we pick 1/3, and then 4, 8 minus 10 is an orthogonal basis for W. Okay, let's do a checking whether it's correct or not. Or maybe we did mistake again. So let's take 122 dot with 4, 8, 10. Okay. So what's this? So you get 5/9. Okay. 4.1 for 8.2, 16. 2.10 minus 10 get minus 20. So you get 0. Okay. Yeah. Right.
Sorry. Sorry.
Okay. So from here you get an orthogonal basis. So if you want to get orthonormal, what do you do? If you want to get orthonormal basis for orthogonal set, what do you do? Orthonormal. Just divide the length. Okay, so divide by the length, you will get the orthonormal basis. Okay, is okay? Okay, okay, let's do one more exercise before we go into break. So let's do this exercise here. Now this one we have three subspace spanned by three vectors. Okay, so you got additional one. So how do you find the three orthogonal vectors here? I let you crack your head first. You know how to find two, right? Okay, now how to find three. Yeah, try and think about it. Try calculate. Try start calculate first, and then see what you do will match up with what we discuss later. So you can definitely find the second one, but how do you find the third one? Try calculate the second one first while you are thinking. Try start calculate the second. Find the two orthogonal vector first, and then try find the third one. How many of you have already found two vectors, two orthogonal vectors? How many of you have already found two? Or you have found all? Okay, let's discuss. If you start with x1, maybe you can check answer with the answer here that I copy here. So let's say we fix our v1 to be x1. Okay? So everything else we want to project onto x1. And what I do is, okay, maybe we just put some formality. So we look at the span of x1 first. So we look at the line or just the span of v1. Okay. If you are orthogonal project on x1, you can check with this answer here. So let v2 be equals to x2 minus the orthogonal projection of x2 to w1. Okay. So now how we do is we take x1, okay, and then project x2 to x1, and then take the difference. Okay, become the orthogonal part, which is the orthogonal complement of x w1. So what is this? So s2 is minus s2 dot v1, okay, v1 correct, over v1 dot v1, okay, which is equal to, okay, I skip all the calculation. So which is equal to this. Okay, maybe write in this way is easier. Minus 3, 1, 1. Okay. So now you got two orthogonal vector. So you got the third one. What do you do? Okay, let me draw it out. So you got two orthogonal vector here. Right? So v1 and v2. So you got the third one. Okay. Third one. What do you do? Huh? Yeah. Do what? Sure. Yeah, you look at the plane. Yeah. v1, v2 form a plane. Yeah. You look at the span. So you can project the third vector orthogonally to the plane. Okay. Then after that, you split, you find the orthogonal vector that is orthogonal to the plane. Okay. So in formula, what do you do? You do. So let v3 be x3 minus the projection onto the plane. So let us fix the plane. So let us fix the plane first. Let's get the plane done. So W2 is the span of the previous two V1 and V2. Okay. So you need to project your S3 to W. Okay. But what's this formula here? Remember the formula? If you want to project to the subspace, what do? You need to take the inner product with all the bases. Okay, with all the bases. So what do you have here? You have x3 dot with v1 v1 dot v1 times v1 plus x3 dot v2 over v2 dot v2 and v2. Remember that we can get this coefficient by inner product exactly because v1 and v2 are orthogonal. This is how we set up them. That's why we can use this method to find it. Okay, makes sense? Okay. Okay. So what's this? Maybe skip the calculation again. Or what's this? Let's see. Okay, you can check if you want, but let me skip the calculation. So it is 1 over 3 over 0 minus 2. Okay. So what? So these three vectors form the orthogonal basis for W. So let me copy it. 1, 1, 1, 1, and minus 4 times minus 3, 1, 1, 1, and 1 over 3, 0, minus 2, 1, 1. Form an orthogonal basis form for you. Okay. So let's say if you have 4-dimensional span, what do you need to do for the fourth one? How do you find the fourth orthogonal vector? If you have the fourth one, okay, that's too complicated. Now you already have, okay, from this example, right, you can find 3 orthogonal vectors. Okay, how to find the fourth one? How to find the fourth one? Huh? Yeah, of course. I mean, how you continue, like how you inductively use the process that we have discussed just now. So for the second one, we project, or to find the second orthogonal vectors, we project it to the first vector and then take the difference, right? For the third one, we project to the 2-dimensional space spanned by 2 orthogonal sets, and then we take the difference. So now how to take the fourth one? Project the fourth vector to the 3-dimensional subspace and then take the difference. Okay. How to do the fifth one? I take the fifth vector, project to the 4-dimensional orthogonal spanned by orthogonal subspace spanned by orthogonal vectors, and then take the difference. Okay. How about the sixth one? I take the sixth vector, project to the 5-dimensional orthogonal subspace, and then find the difference. Okay. So this is what we call the Gram-Schmidt process. Okay. So if you got P vectors, okay, if you got the basis of P vectors, so what you do is you take one of them, make your V1, okay, and then take a second one, project on V, okay, this part, project on V, or let me write down. So you project, orthogonal project, x2 on V1, okay, and then take away S2. Okay, make sure you take in the right order. Order is very important. So this is orthogonal to X1. And then how about the second one? You take S3, take away the projection of S3 onto the subspace spanned by V1 and V2. And then here, spanned by V1 and V2. Okay. So in general, what you do, you take the P vector, the number P vector, take away the projection of the P vector orthogonal projection onto the previous T minus 1 subspace. T minus 1 subspace. V, yeah, T minus 1 subspace. Okay. All right. So when you want to project your vectors into p-dimensional, then you need to take all the inner product with every basis vector and then divide by the length. Is it clear? This Gram-Schmidt process is the main takeaway for this section. This section here, the main technique you need to learn is this Gram-Schmidt. So I'll give you a set of bases, how you produce an orthogonal set of bases. But this is the main takeaway. Only after you learn Gram-Schmidt, only you can say that you attended linear algebra course. Yeah. Okay. Yeah, Gram-Schmidt process very important. Gram-Schmidt. Okay, so give you a basis, you can turn it into an orthogonal one using Gram-Schmidt process. Okay. Okay, let's take a break until 5:11. Then come back. Okay.
I skip that row? Eh, Ranjan haven't signed off. Eh, pass back. Pass. They haven't signed. Pass to the back.
I see some of you are struggling taking this course, even though you are quite good or you are quite hardworking. Because my prospect for you is so my how to say my expectation for you is you can compute, you know what you're computing, but maybe you cannot show why this is true. Okay? Because this is kind of test. So my expectation is after you attend this course, you will know how to compute first of all. Second, you will know what you are computing, why you are computing. Okay. Maybe you cannot tell people why it is true, but you can tell people what is going on. Yeah, this is my expectation. Uh, uh, Maybe still seems a bit too ambitious because uh, I saw some of you quite struggling, but there's one more week left. So after this week, next Tuesday, you should be free. um, yeah. Okay. Yeah. If it is in the proper course, then maybe we need to learn a bit why. I mean, improve. Sometimes it's easier to say, then I will just say it. Sometimes if it's not, then we cannot do it technically. If it is the maths course, then we will need to do everything in detail. Calculation, right? Calculation, you will see that sometimes not doesn't care much about calculation, because really calculation have to done by your own. Everyone will do different mistake, so I cannot control it. Okay. So what I can control is how you do it. When I say how you do it, right, it's not that I need to tell you step by step how you do it. Okay? I need to tell you the general principle. Okay, it's not step by step. Okay? When I study mathematics, right, we almost don't finish tutorial question in class. We never finish tutorial question, and they don't really care whether you finish or not. So meaning, even if you finish everything in class, it doesn't mean that you have achieved something. No. Okay. So, I mean, yeah, this is like real life, right? Life is going on. It's not like get it done. No. So it's like keep processing, like keep progressing, not processing, progress. Okay. But each time you need to have new progress. That's for sure. Okay. First time you stuck here, next time you shouldn't stuck here anymore. Okay. Yeah. Okay. So one more thing I still want to convince you, so because we need to use this principle again. So let's talk about the nearest point on W to B again. Okay. If your B lie in W, okay, of course the nearest vector to B is just B itself. Yeah, because B, if B is in W, then B minus B is just 0. Okay. Let's say your B is outside the subspace W. Okay. So what's the nearest vector in W that is, yeah, what's the nearest? Okay, why don't become a straight line? Okay, so we call it B hat. Okay, so what's this B hat here? This B hat here is the orthogonal projection of B, B to W. Okay. Okay. So why is this the shortest one? Okay. Let's say we pick another W here. Yeah, just take one is enough. Take one. Okay. So we try to compute what is the length of B minus W1. Okay. So what's this? So diagrammatically, it is something like okay, maybe make it shorter to make this diagram nicer. Okay. For aesthetic purpose. Let's put this. So the length should be this vector here. Agree? Agree or not? Agree. The blue dashed line is the vector of difference between B and W1. Agree? So you take the length. Agree or not? Agree? Right? Okay. So I need to argue why this length is greater or equal to B minus B. Okay. In fact, we can give the formula. Okay. So how to relate these two numbers? Anyone have any? How to relate? How to relate these two dashed line here? Yes, triangle. Okay. How to draw a triangle? At where? At the missing edge. At the missing edge here. Okay. And when you add here, actually you realize that there's another 90 degree here. Okay. So which means what? Which means what? Which means the blue one, the name is very long. Maybe I just put a long name here. So the length of the pink dash line is what? B minus B hat, right? Okay. Blue dash line is what? B minus W1. How about the orange line? You know how to find the length of the orange line? It is the difference between B hat and W1. Okay. Okay. So by the Pythagoras theorem, what is this Pythagoras theorem? Pythagoras theorem say what? B minus B hat squared plus B hat minus W1 squared equals to B hat minus W1 squared. Okay. Okay. So when you compare B and B hat and B hat and B, they differ by B hat minus W1. All right. Okay. This is the square of them, but we are comparing the non-square version. But after square, you can compute it. Okay. Also, you can see it here. If you try to like throw this inner product away, right? It's really B minus B hat plus B hat minus W1 become B minus W1. Okay. Actually, this is some, yeah. I mean, on the level of vectors, right, they are equal. But when you put inner product, then something whole on the level of the length. Never mind if you don't understand what I say, but if you can imagine what I say. Okay. Next. Okay, so why I say this is important? So because now we want to change the W here into a special space, into a space which we call the column of A. Okay, column of A is a subspace, right? So we want to change W into a column of A. So we make it a column of A. Okay, column space of A. So after we make it a column space of A, so what is the interpretation to be had now? So it is this segment here. So let A be an M times N matrix and B a vector in Rm. So you can think of the diagram I drew just now. Okay. So a least square solution of Ax equal to B is an X in Rn such that B equals to Ax less than equal to B minus Ax for all X in Rn, and B minus Ax hat is square is called the least square error. So that means they want to make this B hat, right? Then they want to make B hat into, they want to find a solution of A to B hat. Okay. So what's this doing actually? Okay. So how should I tell you? Okay, maybe use this example as an exercise. Okay, is this example good? Maybe this example. Okay, I use this example because this example can serve for two purposes. Okay, so let's use this example here. Okay, so is this a consistent system or inconsistent system? We go back to second week material or first week material. Okay. So is this a consistent or inconsistent? Still remember how to do row reduction? No need do row reduction also can solve. Okay, so is this a consistent or inconsistent? Consistent. Consistent or inconsistent? Let me set up something, then I will tell you a true story. What's this? Consistent or inconsistent? Inconsistent. Inconsistent. Is it so fast? Let me see. A7. Okay, I think it's inconsistent, so let's do it one more time. I think we should get the result. So, which one is better, faster to calculate? This one I hate calculation. This one is just some junk. So I'll divide by 17, 13. Okay, stop here. I think this one is non-zero. Should be enough. Stop here. Let's stop here. I want to deal with this. Okay. So you can see that this is a 4x2 matrix. Okay. You have to solve 4x2 matrix. So 4x2 matrix is an over-determined system. Okay. That means what? You got more equation than your solution. Okay. Variable only got 2, but your equation got 4. Okay. Usually over-determined system is inconsistent. Also, from the number of pivot you can see, at most you can get 2 pivot. So if here 0, here is something non-zero, then most probably it's inconsistent. Okay. So this is inconsistent, but we still want to solve it. Okay. We still want to solve it. So what to do? We find the closest solution to B. We find the closest solution to B. Okay. So what does this mean? So we project to something that A can solve. We project to the space where A can solve it. Okay. And it is the closest one to B. Okay. I don't know why they want to do it, but it seems like this is very important in applied sense. So you need to project to the column space of A. Okay. Where you can write it as a linear combination of A. Okay. So let's show you how to do it. So let's make this more precise. Okay. So since we cannot solve for B, we solve for something really close to B. Okay. So first we need to project our B into column space of A where we can solve it. Okay. So what we do first is we project our B into column of space of A. Okay. Can we do this? Can we do this? Let's spend 2 minutes. Can we do this? Yeah. Do this. Project B into column space of A. Let's do this. Okay, let me tell you another thing is maybe you have some mindset that you always have to do it correctly. Okay, it's fine you do it wrong, but make sure you know why you are wrong. Okay. each step again. But for you, you have to calculate first before you skip. Because I calculated it before. But I don't know it's correct. I think it's correct because I used two ways to compute it. I'll tell you the second way later. Stop this. Hello. Anyone got the same step with me already? Got it? Got it? What was the end answer? Please tell me. I don't have it. Huh? What's the end answer? Huh? You got it? You too? Not yet. You got it? You got it? Okay, so what's B hat project orthogonal projection of B? Wait, -1. Okay, 1. 5/2. Yeah, okay. Good. Okay. So now we have project our B into something A can solve. Okay. And this is the shortest distance with B. Okay. We already showed it just now. So now we want to solve for this new B here. New B. Yeah, it's a new B. It's new. Okay. The new B here. So how we solve this? So let's call this so let's call all x s hat as the solution to approach called A B. Okay, that is the least solution B. Okay. So what is S hat? So what is S hat here? So what's S hat? I think we need to solve it. To solve this, then you really need to do the row reduction again. You want to skip the step or you want to calculate? You want to skip the step or you want to calculate? Skip the step or you want to calculate? You just need to do the row reduction thing. Want to calculate? Calculate. I give you 2 minutes. Calculate this. It's a 4/2. So we put the augmented matrix out. If someone finish calculate, also check the newbie projection of the orthogonal projection. Okay, I don't want to do this calculation. You do it. I got the final answer. So we will continue if everyone got this solution here. Or you can do it by inspection if you want. Because just 2 times addition. If you are pro enough, you can do inspection. If most of you got this solution, then we can continue. Yes. Okay, one of you got it. Okay, based on this answer, I can know my solution. This. Okay, everyone got? If not, you just try. It's not, there's no trick here. Just do the raw reduction. Okay, all right. Okay, let's continue. Okay, so we got this solution here. Okay, so this is the solution. This is the least solution to B. Okay, so meaning when you apply A to this solution, you get the projection of B onto the column of A. Okay, so remember the main question is we cannot solve AS equal to B, but we can solve the closest answer to B. Okay, closest answer to B. The closest answer is the projection of B onto the subspace spanned by column space of A. Okay, so this is the main takeaway. So I just now I mentioned that this is the second way to do it. Okay, so the second way is this magic here. So the set of least square solution of AX equal to B coincide with the solution of the normal equation. So this thing is called normal equation. So what's the normal equation? Is ATAX equals to ATB. Okay. So instead of solving AX equal to B, you apply AT on both sides and then solve it. Okay. Maybe you think that it is harder. Okay, let's try this technique to the same question again. You apply AT to both sides and then try to solve it again. Okay, try to solve it again. Try to solve the exact same question, but apply AT to both sides. Try to solve it. Solve it. You apply AT to both sides. Is it? If you 1 more minute, 1 more minute. Try apply AT to both sides. See what happened to the matrix and what happened to the vector. Okay, and then try to solve for x again. Do you guys see the matrix become smaller? Because 2 times 4, 4 times 2 squeezed down to 2 times 2 matrix. Becomes smaller. Okay. And then you realize that actually it's a diagonal matrix, right? So if it is a diagonal matrix, determinant not zero, you can find the inverse. And then you can find the solution. Take the inverse and then solve for the solution. No need to go to the raw reduction anymore. Does everyone get the same solution? 2, 1 over 2 using the same method? Got it? Anyone not getting it? Okay. Yeah. So, why is this true? Still got time. Never mind. Yeah. Are you curious why is it true? Okay. So it is true by algebra reason again. Okay. So if you keep I don't believe if you keep computing, you will see why it is true. Okay. If I give you 10 questions, ask you to see that these two solutions are always get the same, I don't believe you can know it without seeing what is going on in the algebra. What are you multiplying? Okay. So to know why is this true, right? We need to understand that actually, okay, let me copy down what we have first. So, we have S hat solve the projection of code A, B. Okay, this is what we have. And then we say that this thing also solve ATA, ATA, what? ATA S hat equals to AT of B. Okay, this is what we say, right? Okay, so what is going on here? You see, there's projection of B. There's B itself. So ATB, no need to project out. Just use the normal B and then apply AT. And then the other side also apply AT. And then we can find the same X. Huh? Y. Yeah, y. I'm going to say Y. Yeah, I'm going to say Y. Yeah. So one way, if you found the ATA very hard to compute, then you go to find the projection. If the projection is very hard to compute, then you use the ATA method. Okay. So why are they equivalent? Okay. So why are they equivalent? First, you need to notice that. So first notice that minus a x hat is orthogonal to co-A. Okay. Does everyone agree why b minus a hat is orthogonal to co-A? What is a hat? A hat is orthogonal projection of b. So b minus a orthogonal projection of b. So you get something orthogonal to the column of A. Right? Make sense? So B minus orthogonal projection of A get something orthogonal to the subspace. Remember the diagram? Yeah, diagram. Okay. You project, you take the difference is orthogonal. Okay, right? You project, you take the difference is orthogonal. Subspace. Okay. For now, okay. So if it is orthogonal to column of A, just take any one of them. Okay, take AJ is any column of A. Orthogonal mean what? You take the inner product, you get 0. So you take the inner product of column of A and B minus AX, you get 0. Okay. So inner product translate to vector multiplication is what? AJ V transpose multiply with AX. Okay. Is that remember? Okay, I just put here to remind you, U dot U is equal to UTU. Okay. Okay, all right. Okay, so in this case, we can collect all the column together. Okay, we collect all the column together to form A. So it becomes A transpose. Okay. And then you just multiply out the A transpose. And then we get ATAX equals to ATB. Okay, so this is the instant where I tell you, if you do 100 over time calculation on both sides, you still won't see the calculation from the number. What you need to extract the information out is what vector you use. Okay. What kind of vector you are using to calculate. This is algebra. No number here, man. There's no number here. Number is not important. Okay. If you just look at number, you can never see this game. You need to know what vector you are using. Only you can see this principle here. So this is one particular instance why I advocate the algebraic structure is important than calculation. Okay, I didn't say that calculation is not important. It's important, but what is going on behind is even more important. Okay, yeah. Okay, agree. Okay. Okay, so before we end, we go into more abstract stuff, but it's not tested. Okay, so before I launch into this inner product space, let's go through what we did for Rn. Okay, for this section here. So we introduce orthogonality. Okay, what's the use of orthogonality? What's the main thing you need to learn in the process? What's the process, the main process you learn? Remember the process that I say you must learn before you leave the class. I mean, finish this course. What's that process? Oh, very important one. I think it's a two-guy name. What's the process? Gram-Schmidt. Okay. So you have this inner product. You can use the Gram-Schmidt process to build orthogonal bases. Okay. Right? Is that right? So why orthogonal basis is important? Because there's a special way to find the coefficient for every vector. Okay, you don't need to do row reduction, don't need to do Cramer's rule, all those. Okay, you just use inner product to compute your to express your vectors as a linear combination of orthogonal bases. Okay, so this applies to every space that have inner product. Okay. We call that inner product. We call inner product. What's the inner product? Okay, so what's inner product? So you will think that the inner product is take two vectors and they give you a number. Okay, not just that. Inner product is the thing that satisfies these four properties here. Once you have inner product that satisfies these four properties here, you can do Gram-Schmidt. You can do check orthogonality. You can compute the length. You can do all this stuff. As long as your vector space have this inner product, you can do whatever we did just now. Okay. So sometimes you will see the question in different vector space, for example, polynomial, set of infinite sequences. If you manage to define an inner product, then we can do all the Gram-Schmidt length, compute distance, compute. So what's the distance between two polynomial functions? Yeah, what's the distance? Depend on the inner product you define. Then we can give distance between functions. Yeah. Right. Have you think of distance between functions before? Yeah. Okay. So inner product, as long as you have inner product that satisfy these four properties here, you can do whatever we do on R. Okay. You can find basis, you can express your element in terms of the basis, and then so on. Okay, that one is for vector space, but you can find orthogonal bases more importantly. Okay. Okay. And maybe should we do this? Okay, I will do this Okay, I think this one very important because already got like 4, 5, 7 students come and ask me how to read the notation in the tutorial question. Okay, maybe we will do the first one before we leave. The second one maybe I will leave it not as exercise, but I will show you the solution because in this course we are not focused on using the property of inner product. So I just show you how to prove it. But A is important because you need to know how to read the notation here. Okay, so this will also solve the question that you don't know how to read the solution in the tutorial. So let's say we have two polynomials in the set of polynomials of degree at most 2. So define the inner product. If you give me two polynomials, okay, I give you P0 times Q0 plus P minus 1 times Q minus 1 plus P1 times Q1. Okay, so the things that they assume here is you know how to do function evaluation. You know how to substitute for function. Okay, so what do I mean by that? For example, it asks you to compute the inner product between these two specific P and Q. Okay, so now we want to compute the inner product between P and Q, which is equal to the inner product between 1 minus 2t plus 3t squared, comma 1 plus t squared. Okay, so in this case, what is P0? Okay, so since Pt equals to 1 minus 2t plus 3t squared, what is P0? Okay, P0 is when t equals to 0. So it's equals to 1 minus 2 times 0 plus 3 times 0 squared, which is 1. All right. Okay. How about, so you require P0, P minus 1, and P1. So what is P minus 1? So P minus 1 is when t equals to minus 1. So it's 1 minus 2 times minus 1 plus 3 times minus 1 squared. So what do you get? 1 plus 2 plus 3, 6. How about P1? P1 is 1 minus 2 times 1 plus 3 times 1 squared, which is 2. Okay. So how about Q0? Q0 is 1. Okay. Q1 is Q minus 1 is plus 1, correct. Q1 is 1. Okay. So if you put these two together, put these two together, you get 1 times 1 plus 6 times minus 1 plus P1 is 2 times 1, which is 4 minus 2, right? Is it? Yeah. Wait. 3. Minus 3? Minus 3. Okay. Okay. So using this inner product here, we can see that these two these two polynomials have a distance, which is minus 3. Is it positive? Okay, real number. Okay. Yeah, minus 3. Okay. This is not distant yet. This is just inner product, right? Distant, you need to take the norm. So how you define the norm? So you just similarly you take v dot v, v dot v, v dot v, and then take square root. It's the same, but you need to realize that the inner product here can change. For example, in this polynomial case, it changed to this form here. So if you want to compute the distance between P and Q, then you need to take P minus Q. Okay, P minus Q, and then you compute this length using this inner product, not the vector one. Okay. So next part is the Cauchy-Squash inequality. So last time we didn't prove. We said that we will postpone it to now. Or not? Maybe you guys not interested. Huh? Okay, I will show it in the lecture note anyway. But the takeaway here is the inner product of U and V is less than or equal to their product of their separate length. That's all. Cauchy short inequality. But actually, the real boss is triangle inequality. Okay? This thing is used to prove triangle inequality. So this triangle inequality is kind of important. Okay? What it's saying is, if you add up two vectors, right, and then you compute the length, it's always less than or equal to the separate length. This is the real thing. Okay, this is actually I think so. This is like Pythagoras theorem. Is a weak. Can I say weak or strong? It's a strong, weak, maybe weak. It's a bit like Pythagoras theorem. If it is equal, then it is the Pythagoras theorem. Is it? Or not really? Okay, this is a non-square version because Pythagoras theorem is square, right? It's square, but this one is a non-square one. Yeah. So meaning, how to say? So this determines how you walk. How you walk. So what's the shortest distance between two lengths? Okay. So we keep saying that the shortest distance is the straight line. Okay. If you walk through this right angle triangle, right? Okay. Even though, let me put in 1, 2, 3. Even though V1 is less than V3, V2 is less than V3, but when they add up and square them, it is actually V3 squared. Okay. So when you try to walk from one point to the other point, right? So make sure you walk in the straight line. As straight as possible. Okay. If you are not as straight as possible, you are doing more work. Does that make sense? Yeah, I mean, if you want to do it efficiently, but if you want to waste time, right, so you need to work as not straight, it's not possible. Yeah, it depends on what you see. Okay. Yeah. Okay. So the inner product part is a more abstract part, but not tested in the exam. Just for you for an extra motivation. Okay. If that's all, tomorrow we'll start chapter 7 and then hopefully finish by Friday. And not Thursday. Thursday, huh? No, we must finish it. There's no way to not finish it. Actually, hello. Actually, there's one point I'm quite happy about you guys. So I increased the, and let me stop this first.